All right, everyone, this is part 2 of our notes on 3.5 exponential models. So part 1, we worked through the bulk of our notes here. We worked through a few examples that involved using our graphing calculator. There's a couple extras here that are built in based on some equations. So one is this idea of logistic growth. The idea that underlies this idea of a logistic growth model is that nothing can exponentially grow forever. There must be some limit. For example, there's only so many, there's only so much resources for animals to consume, right? There's a point at which things start leveling off. The logistic curve actually looks like this, right? It looks like right, you can kind of see how it looks exponential for a while. And then there's a point at which resources start diminishing. So the rate of increase flattens out significantly until it becomes asymptotic. It will actually be a horizontal asymptote. So the formula we use, you can see here, is A equals C over 1 plus A times E raised to the B negative BT. In this case, both A and B will be given as constants, and C is what we call the limiting amount. There's some quantity that we can never get larger than. Our input here is T time. So let's work through this example together. They tell us that the number of people who have become ill with the flu T weeks after its outbreak can be given with a model f of T equals 30,000 divided by 1 plus 20 times e to the negative 1.5 t. In question 1, they are asking us to evaluate how many people became ill when the epidemic began. Well, that is when t equals 0, so really we want to find f of 0. Now in this case, we certainly could plug things in and start moving things around. What we'd end up with is 30,000 divided by 1 plus, well, e to the 0 power will be 1, so it's really 30,000 divided by 22. Now, when we plug that in to our calculators, we get 1,429 people. Now, they established that T is the number of weeks after the initial outbreak. If we want to find how many people were ill by the end of the 4th week, we simply need to evaluate f of 4. Obviously, this one's going to be a little bit harder to do. We will need our calculator, but when we do that, we plug in 4t in our exponent. We will find there will be 28,583 people with the flu. In part C, they ask us what is the limiting size of the population that becomes ill. Well, that limiting factor comes from our numerator, that C value. In this particular equation, that C value was 30,000. This should make sense, right? We couldn't have more than 30,000 people sick in a town of 30,000, right? That's our limiting factor. There's only so many people who can become sick. If we turn to the last page of our notes, we'll find one last example that we need to complete here, and that's about Newton's law of cooling. What we know is that the temperature of a heated object decreases exponentially over time towards the temperature surrounding the medium. All right, temperature kind of works towards equilibrium. I think it's through the process of diffusion, but I might be wrong on that. But we have a formula to model this, and it depends on a few things. C is the surrounding temperature. Right? If we're trying to kind of reach equilibrium with the room temperature, it matters what that room temperature is, if it's 30 degrees or if it's 150 degrees. T0 is the initial temperature that our object or I guess it's usually an object starts at, and there's some K value constant in our exponent. So this is still an exponential model since we have our input, time, as part of our exponent. So let's look at an example together. They tell us that a cake is removed from the oven at a temperature of 210 degrees. So that would be our initial temperature, right? So we would set up our formula with that. It is left to cool in a room with a temperature of 70 degrees. After 30 minutes, the temperature is 140 degrees. We want to find a model for the temperature after T minutes. Basically, we need to find K. We know the initial temperature, we know the surrounding temperature, we don't know what our constant value is. So we're going to set this up. Our initial value, the temperature, the current temperature T is 140 degrees, and we had a surrounding temperature of 70 plus, in parentheses, an initial temperature of 210 minus our surrounding temperature times E raised to the K, and the T value here would be 30. Right after 30 minutes, we have a temperature, right? We've plugged in values because they've said after 30 minutes, we have a temperature of 140 degrees. We're going to solve this equation for K. I'm going to work through this. We know that if we subtract 70 from both sides, we will get 70 equals, I'm going to simplify what's in my parentheses here, 140 times E to the 30K. Well, I can divide both sides by 140, so 1/2 will equal E to the 30K. We can take the natural log of both sides, so the natural log of 2 will equal 30K. So K will equal the natural log of 2 divided by 30. I'm sorry, that should have been the natural log of 1/2. I apologize. Let me make that change as we go. The natural log of 1/2 divided by 30. Our K value would be, as a decimal, negative 0.0231. So what we've found is the actual model we're going to use because we know a lot of the other components. The model we're going to use is the current temperature equals 70 plus 140 times E to the negative 0.0231 T. Sorry about that. Just wanted to make sure we got those numbers ready. Now, what we can do is we can use this model to approximate the temperature after certain values. We can use this model to make more sense of make estimates and approximations about at what time certain temperatures will be reached. In part B, they ask us, what is the temperature after 40 minutes? Well, all we need to do there is plug in 40 for T. So I'm going to take this exact same formula. I'm going to remove T, and I'm going to plug in 40 instead. And all we have to do is plug that into our calculator. It is approximately 126 degrees after 40 minutes. Working the other way will be similar to the process of finding K. When will the temperature be 90 degrees? Well, that's our current temperature. That's going to go into our model of 70 plus 140 E to the negative 0.0231 T. And really, we're trying to solve this equation for T. So we can subtract 70. We can divide by 140, so we'll be left with a 1/7 equals E to the negative 0.0231 T. We can take the natural log of both sides. We would have the natural log of 1/7 would equal negative 0.0231 T. We can divide both sides, and we will find that T will equal 84 minutes. So the big idea here, we do have these models and all the rules that we've seen throughout the course of the unit still apply. If I want to solve for an exponent, I'm going to have to use logarithmic properties. And if I want to evaluate a logarithm, I simply need to plug into that exponent. Thanks, everybody.